Okay, we're going to talk about work and energy. So let's talk about work and energy. So we have a formula that says that the work is equal to the force times displacement. And you use this formula whenever you want to measure the quantity of energy that you waste in a process. For example, let's say you want to move a box, and here we go. This is our floor right here. And okay, this is your floor. And let's say that you have a box right here. Let's say you have this box, and here is your box. And let's say it's a particle, and you want to move it from this place. Let's call this. This is going to be x of naught. So let's move it from x of naught, and let's move it all the way to. So you're going to move it all the way to this spot over here, and let's call this spot right here. This is okay. Let's make it a little better. Let's call this spot x final. And you're going to move your box, all this displacement. This is going to be your displacement right here. Let's call it delta x. And to do that, you're going to apply a force. So your force is going to come this way right here. Let's say this is your force. And that's the force that you apply. Let's call it force. And it's going to be an angle theta right here. So you're going to apply this force, and I'll put the force over here. Let's do the force over here so you can see what's going on with the force. Okay, and what's going to happen? You're going to break it down into components. One component is going to be f of x, and another component is going to be f of y. It's this component that goes this way, and this is going to be f of y. So, and this is going to be your angle here, and this is going to be your force. So you're going to break down this force into components, one that's going to go in the x direction and one that's going to go in the y direction. So you're going to have two components for your force. Why do you want two components for your force? Well, because the one that goes in the x direction is the one that's going to push. And if you multiply that force in the x direction, times the displacement in the x direction, you're going to measure the quantity of work done on the particle, on the box. And that definition, that formula, the formula of work, is going to tell you how much energy have you wasted. If you want to know how much energy you wasted in the process of moving that particle from x of naught to x final, you have to use the definition of work. So f of x is going to be equal to f cosine of theta, and then you're going to plug it over here. So the work is going to be f of x, which is going to be f cosine of theta, and you're going to multiply times delta x. So the work is going to be, you can play around with these factors. It's going to be f times delta x times the cosine of theta. And this is going to be your formula to calculate the work done on a particle. Let's say the force here is 10 newtons, because the forces are measured in newtons. And let's say the displacement here is 5 meters. And let's say that our angle here is going to be 45 degrees. So this angle is going to be 45 degrees. So let's plug in this. So the work is going to be the force. The force is 10 newtons. And you multiply times the displacement, which is 5 meters. And you got the cosine of 45 degrees. The cosine of 45 degrees is going to be square root of 2 divided by 2. So it's going to be square root of 2 divided by 2. And multiply everything. And what do you get here? Well, your answer is going to be around 35.36. And this is going to be Newton times meter, Newton meter. But Newton times meter is going to give you a new unit. So this is going to be equal to 35.36 joules. Okay. Remember that 1 joule is equal to Newton times meter. Newton times meter is going to give you joule. So there you go. So you have measured the quantity of energy that you have wasted in taking the particle from x sub naught all the way to x final. And delta x in this case is going to be 5 meters. And the component of the force that you need to measure the quantity of work done has to be the component which is in the direction of motion. In this case, the motion is on the x-axis. So you will have to multiply the component of the force that goes in the x direction times the displacement, and that's how you get your work. In this case, it's going to be 35.36 joules. And you can also do something else here. Okay, so I'm going to clear this board. This is an example of how you apply the formula for work. And let me clear this to tell you something else. So we have 3 formulas. One that says that the force is equal to the mass times the acceleration. And we just played around with the formula for work, which is force times delta x. And we have this formula that says the final velocity to the square minus initial velocity to the square is equal to 2 times acceleration times delta x. So we have these 3 formulas right here. And we can combine them to get a new idea, which is very important. And the idea is this one. So the force here, we're going to plug this in here. So the work is going to be equal to the mass times the acceleration times delta x. This is a delta x. Okay. Let me make it a little better. Okay. So this is delta x. Okay, there we go. And over here from this formula, this one, final velocity to the square minus initial velocity to the square is equal to 2a times delta x. We can solve for acceleration. So final velocity to the square minus initial velocity to the square divided by 2 times delta x is going to be equal to the acceleration. Then we can go ahead and plug this here. So the work is going to be equal to the mass. And then instead of the a, we have final velocity to the square minus initial velocity to the square over 2 delta x, which is this one right here. This one goes in here instead of the acceleration. And then we have the delta x. And then what happens here is that this guy can be canceled with this one, delta x with delta x. And then you have that the work is going to be equal to, so you multiply the mass times the final velocity to the square over 2. So it's going to be 1 over 2 mass final velocity to the square minus, you do it with the second term. So it's going to be the mass times the initial velocity to the square over 2. So it's going to be 1 over 2 mass initial velocity to the square. And what do you have here? Well, you have a new formula, which is this one right here. And we're going to define the kinetic energy. The kinetic energy is going to be 1/2 of the mass V to the square. And the kinetic energy is energy that shows up whenever something is moving, whenever something is having velocity and it has a mass and it's moving. Well, of course, if it is moving, it has velocity. You're going to find that there's going to be some kinetic energy present. So we can say that the work is equal to the kinetic energy final minus kinetic energy initial, because these guys right here. And what you have here is the work energy theorem. So we can write this one down this way. We can say that the work is equal to delta kinetic energy. And this will give you your relation for the theorem of work and energy. So this is the theorem. This is a work energy theorem. So we call it the work energy theorem. And we're going to play around with this one a lot. There you go. And thank you very much. See you next time.